Ok, buenos días. Estamos en la defensa de tesis de Sebastián Alfonso Nuñez Jara, que va a presentar su tesis sobre la variabilidad espacial del CHEAR de la onda de velocidad y las implicaciones para la liquefacción en la respuesta de un caso de estudio para el terremoto de MAULE del 2010. La comisión está presidida por el profesor Guía, el profesor Gonzalo Montalva, de la Facultad de Ingeniería de la Universidad de Concepción, el profesor Matt Miller, del Departamento de Geofísica, el profesor Rodolfo Araya, del Departamento de Ingeniería Matemática, y el profesor Marco Pilz, de Potsdam, de PZ. Entonces, ahora viene una presentación que va a ser en inglés, después vienen preguntas de la comisión, y finalmente la comisión se va a reunir para deliberar. Así que, adelante, Sebastián.
Ya. A todos y todas, esta presentación va a ser en español, así que estoy atento de todas maneras a sus preguntas en inglés o español. So, yeah. Hello everybody, my name is Sebastián Nuñez Jara, and today I will be presenting my master's thesis named Spatial Variability of Shell Wave Velocity, Implications for the Liquefaction Response of a Case Study from the 2010 MAULE Moment Magnitude 8 earthquake in Chile. Go on, please. So, yeah, the presentation structure is as follows. First, I will introduce the topic and case study through the motivation. Then I will expose the research main and specific goals. And after that, I will explain the methods and result of how we retrieve the velocity structure at the Los Presidentes site. And afterward, I will do the same with the modeling of the liquefaction response at the site. Finally, I will present the research, general discussion, and conclusions. Okay, so earthquake-induced liquefaction is a phenomenon that occurs in soils, typically frequently loose to medium dense saturated sands, exhibit a significant loss of strength and stiffness, and start behaving as a liquid due to the seismic generation of excess pore water pressure. So before an earthquake, we have a unstable condition in which individual soil grains are held in place by frictional or adhesive contact forces, with water filling the space between the grains. In that case, the effective stress at any given point in the media will be the overburden stress of the dry soil minus the pressure that the pore water exerts. During the earthquake, the soil will try to densify due to the shaking, causing an increase in the pore water pressure and reducing the effective stresses. If the effective stresses is close or equal to zero, the soil particles might lose contact completely between each other and go into suspension. And in this case, liquefaction is initiated and large deformations will occur. After the earthquake, the fluid will be, which is could be water or sediments, will flow, and soil will return to a stable configuration. But settlements and soil desiccation will be are often observed. This means that the volume of the media may be different from the beginning. So liquefaction is a very complex and nonlinear phenomenon, and its associated damages and deformations have shown to be difficult to reproduce using either empirical or numerical tools. You can continue. Still, in recent decades, the increased quality of computational structure, as well as the development of cutting-edge constitutive models, have shown promising results in simulating the liquefaction response and observed damage patterns in the both in the laboratory and in the field. For example, here we show a model generated by Brian Luke 2017 in the frame of the Christchurch 2011. And here they did a geotechnical characterization of the site in which they identified different soil units. And with that, and they performed an effective stress site response analysis in order to simulate the shear strains developed at the site. So this is one of the many examples in which numerical models have been used for evaluating liquefaction response. You can continue. So we can say that with numerical models, in general, researchers have assessed the influence of geotechnical properties and seismic motion in liquefaction response. However, this is the gap that this thesis intends to bridge, there is a limited exploration influence of shear wave velocity, spatial variability in liquefaction response. The shear wave velocity, or BS, is defined as the square root of the ratio of the small strain shear modulus and the density of the soil. And in linear wave propagation problems, BS governs the seismic wave amplitude and constrains the stress-strain response of the soil units. In nonlinear problem, apart from that, BS also governs the shape of the hysteretic loops. This implies that when large shear strains occur, the hysteretic loops will tend to be wider and there will be a larger energy dissipation. To conduct our research, we need a case study, and we know that there is widespread evidence of liquefaction observed in the frame of the MAULE earthquake at different level of severity. And we know that there is a well-documented and characterized loss precedent case study where there is actually research that has been conducted in the recent past. You can continue. So here we see in more detail the loss precedent case of the study. Here we have a satellite image at the left of the Concepcion downtown, in which we see the colored dots represent the sites in Concepcion where superficial evidence of liquefaction was reported. The green circle, the green dashed circle that you might see is our site of a study. If we make a sum at this site, we can see that we see 4 labeled buildings A, B, C, and D. These buildings were the buildings that were constructed at the moment the earthquake happened. And at the site, there was a variable and heavy liquefaction damage observed in the form of ground cracks, soil ejecta, as we can see in the pictures at the bottom of the satellite. And also, there was a very large building differential settlements in Tower A. They reached the order of 30 centimeters, and in the building B, they reached the order of 10 centimeters for the building A and B. For these reasons, both of these buildings needed to be demolished and rebuilt after the earthquake. On the other hand, the buildings C and D were not exhibit little to no settlements. They didn't need to be rebuilt. So now that I have talked about a bit about the case of a study, I can present the research goals in the next slide, which are the main goal of this research is to assess the effect of BS spatial variability in liquefaction response by performing an effective stress site response analysis at a residential site that exhibit major liquefaction damage in the context of the 2010 MAULE earthquake. The specific goals are to conduct a geophysical survey at the site of the study in order to record microtremor wave field, to retrieve the study site shallow velocity structure from the recorded data using seismic interferometry principles, to generate spatially heterogeneous BS soil domains from the known site velocity structure using Gaussian correlated random fields, to perform site response analysis BS 2D models coupled with a proper site geotechnical characterization, constitutive model, numerical model framework, and boundary conditions, and lastly, to compare the simulation results at different degrees of BS spatial variability in terms of pore water pressure generation, shear strains, volumetric strains, and vertical settlements. So as for the first stage was the data collection stage, in which we conducted at the site 5 geophysical surveys from November 2021 to December 2022. We focused in the area between the buildings A and B, where we placed a 3-component high-frequency seismic tremino instrument at 50 different positions depicted in the scheme as magenta triangles. The sea and stars represent the location of past geotechnical explorations carried out, and the dashed line going from T to T' represents the cross section that will be used for numerical model in the next stage. You can continue. So as for the data processing, for each synchronous which are represented by the straight lines that connect two of the triangles, we calculated the cross coherence using the Welch method. We feed the CC waveform to a Bessel function from which the dispersion curve can be derived using the Aki spectral formulation, spatial autocorrelation method. And from that, we obtained 123 dispersion curves aligned with the geology of the site, which are shown in the plot of the. Overall, the dispersion curves are consistent with very shallow and soft soil conditions. You can continue. So here I show some of the velocity profiles derived from the dispersion curves. These curves were inverted using a genetic algorithm, which is a nonlinear part probabilistic scheme, and we show here at the top panels the 1D profiles at three different dispersion curves at the bottom that represent interstation distance of 17 meters, 35 meters, and 22 meters. The red profile is the best solution in terms of fit, and the gray profiles are the solutions that exhibit also lower misfits, and they are used to constrain the 1D profile model uncertainty, which is actually the dotted blue line that's also shown in the panels. From all the dispersion curves, now what we did in the next slide is that we generated a methodology to retrieve a 3D site velocity structure. So we divided this site in cells, in rectangular cells, and we merged all of the 1D profiles that go through to each of the cells, and with a weighting scheme that took in account the profile uncertainty and also the length of the ray. So what we see at in the color coded rectangles, we see that the average shear wave velocity profile at depths of 0 to 0 to 10 meters, 10 to 20, and 20 to 30 meters. And this is the velocity structure we retrieved. We can see that, and it's most noticeable in the part of 10 to 20 meters, that at the bottom cells, and in the middle, we can see that the shear wave velocity, the BS, is slightly lower. At the cells that are adjacent of the buildings, the velocity is greater, actually. And in the zone in between the buildings, at the middle, the velocity is like a kind of like in between the what I mentioned before. So we found that this is consistent with what we actually know about the site, because at the south cells, is the part is the part of the softer conditions where the site. Can you hear me well right now?
Yes. Yeah.
Okay. Yeah. So at the bottommost cells, we got is the part where where the cells with lower ds shear wave velocity we can see, and this is the part that was probably not reconsolidated after the earthquake, and it also most close to the street. On the other hand, in the cells that are adjacent to the buildings was the part that was heavily reconsolidated after the rebuild of the towers, and also the zone that in the middle is something what we expect that. So in the southern in the panel of in the bottom left, we see all the profiles that are correspondent of each of the cells, and we select a representative profile of each of the three conditions that I have mentioned. The black profile is represented directly adjacent to the buildings, representing stiffer conditions. The red profile represents the cells south of the building, representing soft conditions. The blue profile represents the cells in the ground area between the buildings, which is intermediate conditions. For our numerical modelings, we considered the red profile because it should be the most representative of pre-earthquake conditions. Is the one that was not reconsolidated after the earthquake. So you can move to the next slide. Yeah. So for the numerical modeling setup, we take the 1ds red profile, and we generated perturbations using especially anisotropic correlated Gaussian random fields. So what we see here is a benchmark simulation of the site, which we enforce special DS heterogeneities in a region of interest, where at the lateral boundaries in the left and the right, we enforce a 1D velocity profile where the variance was set to 0. So yeah, in total, we considered 5 different levels of BS variance, going from 0.075 to 0.275, going from very little variance, low variance to high variance conditions, 20 numerical simulations per level of variance, making 100 in total. Also, we input the ground motion at the bottom left node of the soil domain by amplifying to a depth of 50 meters a strong motion recorded at a station at Conception Downtown. And with that, we simulated the wave propagation problem in a saturated media. You can go to the next slide. As for the numerical modeling, we use the OpenSys finite element framework. For the numerical simulations, we also use the pressure-dependent multi-yield O3 constitutive model for SANS, which is tailored for liquefaction problems. And we fix the ground table at the surface level from data we recopilated from previous investigations. So we recall that the cross-section that we are considering is between buildings A and B, which is goes from T to T', this red cross-section at the plot of the upper right. And we know that the we have here at the bottom left the BS structure of the benchmark simulation, but we remember that this structure will vary in each simulation. So it's like something variable. And we also, in order to simulate liquefaction, we couple our BS structure with the geotechnical structure given from Saldaña et al. 2024. This structure is assumed to be deterministic, and will be the same for each of the simulations. The next slide. So here we show the benchmark simulation, and we recall values for liquefaction triggering should be an excess for water pressure U from now on between 80 to 100%, and shear strains between 3 to 5%. So at the left, we plot the shallow part of the model, shear strain, volumetric strain, the excess for water pressure, or the RU, and the vertical settlements. We see that there is a clear concentration of strains around depths of 7 to 8 meters, and also close to the surface where the nodes 1 and nodes 2 are depicted. You can see that there is these zones where the large concentration of deformations occur are the zone where the excess ratio tends to be higher. Also, around node 2, we can see a large vertical settlement which reaches around millimeters. We also can notice that there is a discrepancy, one could say, between a difference between the behavior of the west part of the model and the eastern part, where the western part exhibit large deformation and behavior consistent with liquefaction. The eastern part of the model didn't seem to liquefy at all. At the right plot, we see we plot the time series, acceleration time series, the RU time series, and the stress strain paths at nodes 1 in the upper plot, node 2 at the mid plot, and the node 3 at the bottom plot. We see that there is not in the acceleration time series, but for example, in node 1, we see that there is a clear increase in the RU values, reaching rapidly a value of 100%, which is consistent with liquefaction. And also, if we see the stress strain plot, we see one could say the trademark of liquefaction behavior, which is this very large deformation patterns, loops at very low shear stresses. At the node number 2, we see also an increase in the pore water pressure, but is less dramatic than in the node number 1. And we also see nonlinear stress strain behavior and also we can see some accumulation of deformation after the shaking ends. And lastly, in the third node, we see that the RU values don't go over 50%. So there is no liquefaction behavior, and the stress strain paths are quite one will say that it's linear or quasi-linear. So this is just the benchmark simulation, but we can already see that there is a clear difference in the response of the domain. And now we will address the spatial variability of shear wave velocity in the next slide. So here we plot the cross-section median results of all the simulations at depths of 2 meters for different level of variance. So each of the triangles here, color-coded triangles, represent a different level of variance, going from 0.075 at which is low level of the red triangle, which represent 0.275, which is the high level of variance. And here we can see clearly that the west node's behavior is quite different from the east node's behavior in terms of settlements, strain, and pore water pressure ratio. And we also can notice, especially in the shear strain and the volumetric strain zone near the west nodes, that the more the variability increases, of the VS variability increases, the median response, the median strains tend to decrease. We can see this pattern in the shear and volumetric strains, and it also can be slightly seen in the vertical settlements. On the other hand, we see that there is no significant difference in the excess pore water pressure ratio for the different level of variance. You can continue to the next slide. We also show now the all simulation time series for the Western node, that is the most important train and settlements. And we see here all the time series plot in gray, and we see the median time series at the different level of variance, color coded with the same colors that in the previous slide. And we see clearly that there is a decrease in the shear in the shear, maximum shear strain as the variability increases, and we also see the same pattern for the volumetric strains. That is the median response. This also can be seen for the vertical displacements time series at the end. And however, we can see clearly that the excess pore water pressure ratio time series seems to be amalgamated together regardless of the variance. So we can see that we can infer that there is no significant change in the pore water pressure ratios caused by different level of BS variance. In the next slide, we plot the same, but now for the eastern node at the same depth, and we can clearly see that the regardless of the level of variance, all of the time series seem to be amalgamated together in terms of strain, shear strain, vertical displacement, and excess pore water pressure ratio. And even though there is a slight difference in the volumetric strain, if we see the order of magnitude of the volumetric strains, it's quite negligible. So yes, now we can infer that there is a different that the BS variabilities have a different impact whether the soil is evidencing liquefaction-like behavior or not. And this is what we are going to tackle now in the discussion. So first of all, the western and eastern node exhibit a distinct behavior, and we recall from the geotechnical characterization plot in the bottom that the western nodes, the soil units exhibit a low relative density. And we see the median strain and settlements tend to decrease as variability increases. On the eastern nodes, on the other hand, we have more concentration of dense soil units, remains relatively unchanged. And infer from our research is that the BS spatial variability might not alter the soil's intrinsic response to liquefaction. This will be mostly controlled by the soil geotechnical properties and the earthquake loading. I think this is an interesting and important finding of our research. And now the next topic I want to talk in the next slide is that about the attenuation of the liquefaction response at the western nodes. So our results show that the BS variability influences the liquefaction response when nonlinear behavior is already ongoing. So when nonlinear behavior starts, because of the which is controlled mainly by the geotechnical characterization, it seems that increasing BS variability attenuates the maximum settlements and strain developed. So for a given BS value, we already know increases at larger shear strains, as I talked about that in the motivation. So I provided this a little scheme on how I understand the problem. And if we have a 2D medium with low BS variability that is subjected to large shear strains triggered by earthquake-induced liquefaction, the soil overall stiffness will decrease slightly, and there will be a minor damping. And this will signify a small attenuation of strains and settlements. On the other hand, if we have a 2D media with high BS variability subjected to the same shear strains, the soil overall stiffness will greatly decrease there will be a major damping and large attenuation. This will signify attenuation of strain and settlements. We did this for 2D media, but this could to 3D media, and we will, I think, reach a similar conclusion. So lastly, for the conclusion, by inverting dispersion curves of the study site, we found 3 velocity profiles representative of the site conditions. Our simulations show that increasing the spatial variability of PS when nonlinear behavior is ongoing results in a reduction of the liquefaction-induced shear and volumetric strains, as well as the settlements. The spatial variability of PS does not significantly influences the generated excess for water pressure patterns, and this suggests that liquefaction triggering is mainly constrained by soil geotechnical properties, such as the relative density. And we suggest that the attenuation of the liquefaction spatial variability increases to an increase in the hysteretic damping of the soil as nonlinear behavior increases. In the frame for seismic hazard assessment, the consequences in terms of the liquefaction-induced settlements and strains, as we show in our results, are slight but consistent. Despite of that, this study might encourage researchers in the future to thoroughly characterize the velocity structure of a site when conducting site response analysis, because PS heterogeneities might significantly alter the dynamic response of the liquefiable soils. So this was my presentation. The next slide is the bibliography. And thank you very much.